So a few years back, you may recall, many of you may have attended, where the program committee had a presentation on when does the energy industry think it has the physics and algorithms to consume an exaflop, or needing an exaflop to actually do subsurface imaging. I think if we said 2020, we would have the necessary physics and algorithms that would demand it. And a little bit of an update before we go into the panel here about what Scott thinks about that.
Okay. Yes, so I think it was 7 years ago that we did a first projection forward on some applications, and then last year reviewed that and confessed where we were wrong and touted where we were right, and it was a pretty mixed bag. We were asked to do a similar kind of prediction again this year, and Sverre and I put this together. What I'm going to do is look at the process of the seismic imaging, which is most of our compute cycles. It's what we spend. It's what we use to convert the acquired seismic data into an image of the subsurface that has value to us. So what I'm going to do is talk about some of the scaling of the data sets and the methods that we can use to calculate seismic images. A typical seismic data set is basically 5-dimensional, a 2-dimensional array of sources where for each source we collect data at an array of receivers over something like 10 seconds in time sampled at a few milliseconds. And if you put those numbers together for 100,000 sources and tens of thousands of receivers, you get something like a typical prospect level survey would be 10 terabytes. And then what we do with that is we spend most of our cycles on dealing with the wave propagation of that data. Take a source, simulate it, back propagate the receiver data, correlate them to find the reflectors, and then do that for every single source, all 50,000, 100,000 of them. In the industry lingo, that's called your pre-stack reverse time migration. And to give you a sense of the scale of the computational domain we might use to image a single one of these sources, here's the 610 loop. And the overall size of the area is a couple of tens of kilometers. And the resolution that we then get out of these images is about the size of a typical suburban yard. Not terribly high resolution, but that's what we get for typical numbers, where we have that couple of kilometers of scale of the target that we're after, and a frequency that's around 30 hertz, plus or minus factor of 2. And if you sit down, calculate the size of the problem, the memory that we'd be using, it's about 1 billion points, or something in the tens of gigabytes of memory. And that's for a simple isotropic medium. Then you simulate that over the time of the recorded data, and you get something like 10 to the 13th space-time points. And for something like 100 cycles per point, it gives you about a petaflop of compute. Then looking at some of the scaling laws, just to get a sense of how things change when you vary some of the quantities of the problem. If you're varying the target to the depth of the target, the scale of that computational domain we were just talking about, or vary the maximum frequency that you're concerned with, well, the compute goes as the 4th power of those variables. And of course, it scales directly with the number of sources that we're using, which is determined by acquisition. Then a couple of the other factors that sort of show up in the problem is what level of complexity of material are you using? The material could be isotropic. The industry over the past decade or so has gone from isotropic to VTI to TTI. And TTI right now is about the sweet spot. That's what most of our models are built out of, tilted transverse isotropy medium. What's on the horizon, what many of the companies represented in this room have codes for, is also orthorhombic. But I think almost all of our imaging is still TTI, not going to the extra cost and complexity of determining orthorhombic parameters. And then one other variable that you can consider is the type of modeling. Are you modeling the medium as acoustic or doing the full elastic? And that shows up with a factor there, which is, we can call that 1 for acoustic, and then a factor that's related to the ratio of P to shear velocities in the medium. And if you, well, you can see that what's going to be really expensive here is going to elastic. But for the variation with type of material is a scale that's single digit, 1 to 8, crudely. One of the things that I did when I was looking at this was try to get an estimate of what is the industry capability in terms of total number of petaflops. I went out there and looked at a lot of the press releases that you can find, and found that a typical oil company, major oil company, who were publishing the numbers, said it's ranged of order of 5 to 20 petaflops. And the seismic contractors, the major seismic contractors, were listing numbers of 10 to 50. And what I did with that is sort of count up what I thought were the companies that had in-house capability, and made an estimate here. I got somewhere between 200 and 300 petaflops total. I'm pretty sure in this audience, though, there's somebody out there who has a better estimate than I. If you want to tell me about it during the question period or shout your number out now, I'd be interested. But given that kind of scale of compute, you can see that we don't even, if this estimate is at all right, even have a full exaflop in the entire industry right now in terms of our HPC capability. But nevertheless, I think the scale that people have for these machines is about right. A 5 petaflop machine doing the number of shots that the sources we described a little while ago could do 1 TTI acoustic RTM, reverse time migration, in a single day. A very good, capable number that makes a lot of sense. Okay, so far I've been talking about the imaging just by itself, as if you only would do one image given the data that you've got. In actuality, our imaging and model building workflow is a very iterative process. What we do is we take the input data and our initial model, calculate not just one image, but a number of images that's related to the redundancy that we have in the input data. The input data is 5-dimensional, but our image is only 3-dimensional. So we have a redundancy in that we can use to measure the model error and try to correct for it. So we go through this iterative loop, which typically, has been manpower intensive on the update side, but compute intensive for the imaging. And typically what we've done is do tens of iterations of this loop at something like half the maximum frequency, perhaps. One of the interesting things that shows up in this process is that you end up typically having a balance between compute wall clock time and manpower intensive wall clock time. Simply because if you've got more compute, you want to tackle the problem of your manpower intensive component and give yourself better tools so you can reduce your turnaround time. But what we're looking at in the future, and what people are starting to use now, is a more automated process where you're doing some sort of least squares optimization. Two technologies that are typically used here are the full waveform inversion, which right now is done at about half frequency, half the maximum frequency, but you could be doing something like 100 iterations. or you can talk in terms of least squares imaging, which is typically done is trying to determine the reflectivity, and that uses the full frequency that you want, but really can only afford maybe 10 iterations, 5 to 10. So these are a couple of the processes we see as taking over more and more, and doing this in a completely automated fashion. Okay, with all that, what we did, what Surya and I did was we sat down and wrote up a list of various directions that we might go to use the extra compute that would be in an Exaflop system. I'd mentioned earlier the difference between the TTI medium and orthorhombic. It doesn't seem to be giving us a lot of uplift right now, and doesn't even require an exascale, so if it is used, it won't be typically, I don't think, and it's not clear that it's going to give us the value to push us in that direction. The acoustic to elastic certainly could use up those the extra cycles between where we are now and an Exaflop. It probably is going to give some value, but is it going to be enough to actually support the usage of this routinely? As you can see, we colored that yellow with a question mark. We're not really sure. It'd be interesting to see what other people have opinions on that and some of these other technologies or approaches. We can also do things like reduce the iteration time. If that whole loop is now automatic, potentially that could give us a lot of value by reducing the overall turnaround time of the whole project. Similarly, with increased maximum frequency in FWI, that's something that could give us a lot more insight into the material we've got at hand, give us much better resolution. Then we talked in terms of the least squares imaging. That's very likely to give us a better value than we currently have, give us high resolution reflectivity. There's a couple of other technologies we're much less certain about. That's those last three there. Doing things like all the least squares imaging and full waveform inversion that I was talking about earlier, that is doing a local optimization, not a global optimization. If we use those kinds of global optimization techniques, certainly we're going to use a lot more cycles. It's almost open-ended. There's some other technologies, extended model, full waveform inversion, a similar kind of problem. It's not clear what the value is, but the cost is very high and certainly would use up those cycles. Machine learning, lots of question marks. I'm not sure how to evaluate that yet. I think we'll see a talk tomorrow about someone who is using machine learning in the imaging process. Now, that will be particularly interesting. Taking a step away from the applications themselves and what we might do, and concluding here with just some of the concerns about Exascale, always cost and power, the things that really cost us hard cash. Our budgets are usually not highly variable, so we're going to be constrained within similar numbers that we have today, almost certainly. Reliability and fault tolerances have been talked about already, programmability. We've talked about them already and may address them further in the panel. One thing that in reading about the Exascale systems I found was they were talking in terms of highly heterogeneous and potentially one-off systems. One article I read talked in terms of it being a novel architecture or an architecture not represented in the top 500. In other words, definitely something new and different, which is going to stress the tools, the languages, and the workforce that ultimately has to program these systems. One last question is, what are we going to do in terms of systems like these Exascale systems? Are they going to be competitive with the cloud? Or is this going to look much like a cloud-type system? I think I hurried through that fairly quickly, but hopefully not so fast.